Welcome back. This is section 11.2, balanced torques, and this is also section 11.2 in your textbooks. So easy section today. If you have torque, which is a force acting on a lever arm, making something go clockwise, and you also have exactly the same amount of force acting on a lever arm on the other direction, making it go counterclockwise, then the object will not move. So an object will be at equilibrium when there is a balanced forces or no net force. So the idea that there's not a more force in one direction than the other, then it's balanced. The easiest example would be a seesaw. If you have a seesaw where the two children are the equal weights, then your seesaw will balance, and that's one of the cool parts about a seesaw. Children also instinctively know where to sit on a seesaw to make it balance. So if you have a heavier kid on one side, they are producing more torque on that end, and so you would move a heavier person closer to the fulcrum, closer to the middle, and a lighter kid farther out, and that balance and force will balance. That's called balanced torques. So here is a 200 Newton child that's farther away from the fulcrum than a 400 Newton child. You'll see that since torque is actually work, torque is a force acting on a lever arm. Well, that lever arm is just a distance, so force times distance is work. So if you were to have 2 times 6, 200 newtons times 3 meters, you're going to have 600 Newton meters. That's going to be the torque acting to make this go counterclockwise. Well, 1.5 times 4 is going to give you the same balance going clockwise, and so you're going to have a balanced torque, and the board will not move. So if you're looking for two torques to balance, that rod will not tip as long as the two forces are the same. So you're going to have 20 newtons at 80 centimeters, okay? Well, how many centimeters from the fulcrum is it? It's not 80 from the fulcrum just because there's an 80 on the mark. You're going to have, this is going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So each one of those is 10. So away from the fulcrum, I've got 1, 2, 3. I've got 30 centimeters. So I've got 20 times 30, and so that's going to be 2 times 3 is 6, 600 Newton centimeters, okay, which essentially is 6 Newton meters, but don't worry about it. 600 Newton centimeters. Who cares as long as it balances on the other side? So how far away is it from the fulcrum? 1, 2, 3, 4, okay, so I have 40 times what is 600? If I take 600 and I divide by 40, the newtons has to be 15. You have to put 15 newtons at the 10 centimeter to balance with 20 newtons at the 30 centimeter away from the fulcrum on the other side. When you use a sliding scale in the lab, the pieces of metal that you're actually sliding back and forth are not equal in weight to what you're measuring. You could measure something heavier or lighter. All you want is that the torque in one direction is going to be equal to the torque in the other direction. When the torques are balanced, then that object is in rotational equilibrium, and you're not going to move one side or the other. So when are torques balanced? Okay. If I have a teeter-totter and I have a newtons of force at a certain distance of lever arm, okay, then the product of this, the N times D, is going to equal the N times D on this side. It doesn't matter what the numbers are. As long as the products are the same, then you are in equilibrium and it is balanced and you will not have rotation.